This is an incredible question on lines of symmetry, a topic often taught quite early on in school because you can draw the lines of symmetry on a square and on a rectangle. It gets a bit trickier with things like parallelograms and talking about regular polygons, but it's not too bad. But then this is a next level question on it. So it kind of illustrates how any topic can have like tricky questions written on it, basically. Because we've got an n by n square grid. We're going to shade one square in, and we want to know um, how many squares, how many different squares we could shade in, like one at a time, that would lead to there being no lines of symmetry in the shape, basically in the square. So let me give you an example. Let's imagine that I shade this one in, then there would be a line of symmetry because I can just go like that. And if I start shading other ones on, but not at the same time, these are like separate. If I shade that bottom right, there would also be the same line of symmetry. And then if you shade the bottom left or the top right separately, just want to keep emphasizing that, then we'd get this line of symmetry here. So basically there's going to be 0 squares that we could shade in that lead to no lines of symmetry in the grid. And therefore I'm going to start by writing, well, there's 4 in the whole grid, and actually I'm minusing the ones where there are lines of symmetry afterwards, and we're going to get 0. This is going to be a little, it's going to help me with the solution basically. So I'm just getting it in there now. Let's take a look at the next grid, and in fact it might help to draw the lines of symmetry in right at the start. You can immediately see that a line of symmetry goes through every square, so there would always be one. If you shade in this one, for example, there would be a line of symmetry going horizontally, even if you don't get them vertically and so on. So here there's 9, and then I'm actually minusing the 9 squares that all would create a line of symmetry if shaded. And well, not create, but still have, we'd still get a line of symmetry. So again, it's 0. And let's continue this process. So 4 by 4, here's the diagonal. Now this time, I didn't draw it in the first time, but I could have drawn this horizontal vertical ones in. But these do not go through the squares themselves. So really, I've only got, and I'm going to shade these in red, I think. Oh, no, let me stick to blue. So yeah, all of this would actually be shaded. Okay, but now I've got these ones along the diagonal and these ones. But that is actually it, because the horizontal and vertical just go in between the squares, which means I've now got these. If I just shaded one of them, then the resulting grid would not have a line of symmetry. If I shade this one, then yeah, none of them, it wouldn't look the same either side of any of the lines of symmetry that I put on. So in fact, there's going to be 8. And I can see there's 16, and I'm minusing the 8 made from the diagonals, and I'm left with 8 there. Okay, and then I'm going to do the same again for this 5 by 5 grid. We're sort of seeing similar behavior happening, but in a slightly different way. We're getting 0, 0, 8, so I wonder if this one will be 8 as well. Okay, so I can shade in actually all the squares. So the diagonals, all the lines of symmetry go through that point. Okay, but now I've got these. Okay, so I've got 25, and I'm going to subtract. Well, there's actually each line of symmetry I've drawn has like 5 squares going through it, but we've counted this one 4 times, or we should have just counted it 3. So if I take away 20, but then add 3 to kind of account for the fact that I didn't want to actually take away 20, then I'm going to be left with 8. And that is these ones here. Okay. So when I did this question, I think I carried on and did 6 and 7, see what I got, but then I started to think how I could generalize to n squares. In this case, I'm going to go straight for it because we actually have enough information really with these first few, especially when you start looking at the ones at the squares that would give you a line of symmetry when shaded, because if you can work out those squares, you can just subtract them from the total number of squares, a bit like as I've been doing throughout. So let's start by saying if n is even, then the number of different cells that could be shaded, and maybe I call this, I don't know, I'm going to give it a name up here. Let's call it S, in fact. Then hopefully I've defined it enough. I've defined it verbally. S is going to equal, well, it's going to equal n squared, because that is the total number of squares that we have. And then I'm going to subtract the two diagonals. And the diagonals, although they overlap at the very center, they don't overlap in the middle of a square. So for the 4 by 4, I just subtract 4 here and 4 here. And then, well, it's less easy to see here, but here I subtracted 2 and 2. So it feels like I've got n squared, and then I'm going to subtract n, because I'm going to get n along one diagonal, and then n along the other diagonal. So n squared minus 2n. I could factorize it, but I think it's okay to leave it like that. So that's basically my prediction, and you have to explain why, since the diagonals go through 2n squares. Like in the real thing, I'd probably add extra explanation to this, but I'm trying to explain it verbally, and you can refer to the answers for more information. So let's see if this is true. Let's see, in the case of 6 by 6, do we actually get 36 minus 12 to leave us 24? Okay, I'm going to draw my 4 lines of symmetry in, the diagonals, and then these ones down the middle. So you see these ones don't have any impact, actually. Okay, I'm going to subtract the 6 here. And yeah, I'm going to subtract the 6 here. And then all the rest, if I shaded them, would lead to the grid having no lines of symmetry. So we can see there's 6 here, and then actually this is sort of replicated in the other 3 regions. There's going to be 6 times 4, or 24, where it's true. So this is okay. And, I think we've proven it basically. Like I've made a mathematical argument. I'm not just brought this out of nowhere. I've argued that we start with n squared squares, because that's just the area or the number of squares inside, not 1 by 1 squares inside. And then I'm going to subtract n across one diagonal, n along another diagonal, and then that's it. And that is going to be my answer. Okay, I've argued it, I've tested my prediction for 6 by 6, but I can see it must always be the case for an even grid, because you're not going to subtract any for the horizontal and vertical. The diagonals are only going to overlap at the very center, so not in between squares. That has got to be the answer. So as long as you justify it, we are done. And you can see it will also work with the other ones. But I think it's nice to test it on one and see it works. And you could go further if you had enough time in this competition. You could try an 8 by 8 and show you get 64 minus 16, which in fact you would. Now, there's one thing I want to emphasize, and you can't just get this formula without explaining where it's come from. This is a JMO problem, so you can't just like look at patterns and sort of see, oh, does this fit it? It's a quadratic sequence, for example. It depends what maths you know. You have to be able to argue it. And so I wouldn't say I've done a great job of that in writing here, but I feel like I've done it verbally. So just make sure that that is there. Right, now let's take a look if n is odd. We do need to consider these separately because of what happens with the diagonals and the horizontal and vertical lines. You can see with horizontal and vertical, they start going through squares. So we can't just apply the same argument. So if n is odd, then s would equal n squared as before, all the squares, but I'm going to subtract n along one of the diagonals. So let's say it's this diagonal. I'm going to subtract n along another diagonal, But just be careful now because we've subtracted one that we've already subtracted. So in fact, I'm going to need to add one. Okay, that's that bit there. And then I'm going to subtract, say, horizontal. Again, I'm going to be minusing n, but I'm going to have to add 1 because, again, it's gone through a square I've already counted. So that's the horizontal. And finally, I've got my vertical one. I'm going to minus n, but I'm going to, again, add 1. And that has got to work, doesn't it? That's going to always happen for a grid where n is odd. So I'm going to be left with n squared minus 4n plus 3. And let's just check it. I suppose we can shade these ones in. So when n is 7, isn't it? We're going to get 49 minus 28 plus 3. So I'm going to actually be minusing 25. I'm going to get 24, which is the same as the last one. That does seem to be something that keeps happening. Okay, apologies. I've got a slight bit of lag in this video. It's not quite flowing smoothly. But what you can see is that there are going to be 8 little sections of 3. And that is going to lead to 24. Now, it'd be very challenging to, I don't even know how you do it, to kind of do this problem by actually working in terms of the red ones rather than minusing. You're going to get to the same answer, but yeah, if you can get there, it's not going to be anywhere near as easy as dealing with the ones where there are lines of symmetry. So as long as you justify it, I know I've said this a few times, as long as you justify it along the lines that I have, with very, enough detail, then that is the answer to this question. Okay, incredible question. In terms of n, how many different cells could be shaded to get no lines of symmetry when you shade in a single square? Well, if n is even, s is n squared minus 2n. If n is odd, s is n squared minus 4n plus 3.